Let's do the same alkene just so you can see how similar these reactions are. So we'll just have a propene reacting with our HG, OHC2, and some water. What are our other reagents? NaBH4, sodium borohydride. And our product is going to be a Markovnikov addition of OH. Okay? Okay, so I actually had some notes that might help. Oxymercuration. All right, so things that might help you think about this reaction are that our mercury is going to act just like hydrogen or bromine in the bromonium reaction, and it's going to form a cyclic mercurinium ion, just like that bromine one we just did. So our first step is going to be this double bond attach mercury, and I'm going to redraw this first step. So if we redraw the molecule so we see everything that's happening. This double bond is attacking mercury. And just like any other reaction with acid like HCl, once we attack our hydrogen, it pushes 4 electrons off, getting rid of a group, stabilizing this molecule when it gets more electrons. So it's going to break one of these bonds. Top or bottom, doesn't matter. And it pushes one of these acetate groups off. So we're left with an intermediate that looks just like that bromonium ion. So it's going to form a cyclic structure with mercury. And this mercury is still bonded to this piece. And then we have acetate floating around with a negative charge. Good? Okay. So if we look at our final product and we kind of try and think about that bromonium reaction we just did, we wanted OH to bond to the most substituted point. In our previous reaction, to get that Br to bond to a bromonium ion-like complex, we just attacked the carbon we wanted to go to. So what reagent do we have in here that's really similar to OH? Not mercury, probably water. So we have water in the reaction. And the only reason you're using water for this reaction is to get that OH group where it's supposed to be. So since mercury is so electrophilic, I forgot to draw the charge. It's a positively charged ion. It's super electrophilic. Water now has nucleophilic properties. So lone pairs are actually going to do something because it will help with the overall stability of this molecule. So the lone pairs are going to have nucleophilic properties, and it's going to attack the carbon that we want it to bond to. And just like the bromonium ion, when we do that, it's going to break off one of these bonds from the cyclic structure. So this bond is going to break off, stabilizing mercury. And this is an intermediate. So this, everything in brackets are intermediates. So if we keep going, the consequences of all that are we still have our propane. Now there's a water bonded to this bottom carbon. And the mercury is now bonded to the least substituted point, just like hydrogen. So oxymercuration and hydroboration, the mercury and boron act just like hydrogen following Markovnikov rules. So our mercury is still here. What's the charge on water? Positive. So for a lot of these reactions, to get OH addition, you need to put water onto a molecule. When water bonds to it, it's always going to have a positive charge. And you always need some negatively charged base to take the hydrogen off of water. So it's always going to be water adds, and you pull hydrogen off. What have we made during the course of this reaction that is negatively charged that's still floating around? So we still have this acetate here. So I'll make that So this acetate has been floating around this entire time, and its only purpose is to deprotonate water and stabilize this positive charge. So the acetate is going to pull a hydrogen off and stabilize water. And that will give us the end of step 1, which is this. And then we have acetic acid. The acetic acid really has no importance in the reaction anymore, though. It's done its job.
What is the second part of the stop? Do you have the first
I would say it's about right here if you wanted. Everything's pretty stable there, except for the giant mercury that's still stuck onto it.
We could show this in the exam when we need, then we something already.
If you're asked to show the mechanism, he's going to expect all these steps, except for the step that forms the cyclic structure that I didn't show. So everything on here you should show, except for cyclic oil. All right, I'm going to extend the page, so if it cuts off some stuff you're trying to write, just tell me and I'll go back. I think it should be good though. So it's really similar to our final product. Its reaction isn't over yet.
Oh, it's not.
So we're still going. We're really close to being done though. That was the end of step 1. Step 2 is using the sodium borohydride, the NaBH4. Because even though we're really close to having the final product we want, we need to get rid of this mercury complex. And that's the only reason you use sodium borohydride. It's a reducing agent. It's really good for taking stuff off of molecules that you don't want without really changing the molecular structure, which is nice. And this step is just kind of weird. It's just something you have to memorize. So in this reaction, you only use the borohydride once. If you remember, it was NaBH4, but we only use the BH4 part. So if it's missing that sodium, this boron is going to have an overall negative charge.
But you could NaBH.
Yeah, so there's 4 hydrogens. Sorry, I drew it kind of weird.
Oh.
So it is sorry, it's BH4, but one of the hydrogens are important for the mechanism. And this is the part that's kind of strange, so maybe remember that this part is weird, and hopefully that'll help you remember something about it. But it doesn't really do anything we're used to. We're actually going to rearrange sodium borohydride and this mercury complex all at once to stabilize this negative charge. So boron's going to remove this whole piece to get rid of those electrons, and that hydrogen is just going to fill this carbon spot, and it's going to push mercury off. So nothing we've really seen before, which makes it kind of hard to just piece together. So this is a step you should.
So that's taking every spot.
Yeah, it's like trading places with mercury. Right. And then it also stabilizes boron, which is why it kind of happens. Okay, so that's the end of step 2, and we finally have our final product. And if you remember from lecture, the reason we do this reaction is because using oxymercuration can actually give us a really high % yield. So this is the water.